So this set of notes is about, it says first law of thermodynamics. You'll notice the first slide has all of them in there. But we're going to focus on the first law with this set of notes. So these are the 4 laws of thermodynamics. So technically there's the 0th law, then the first, the second, the third. And so again, I addressed this before, but we'll talk about it. They're essentially supposed to be numbered in the order of importance, but unlike Newton's laws, they weren't all discovered at the same time. And so the first law came first, and then the second law, and then the 0th law, and then the third law, if I got my history correct. And so the 0th law got stuck because they're like, well, we don't want to call it first law and renumber all of them, so they just stuck it above it. So 0th law, it says if 2 thermodynamic systems are in thermal equilibrium with a third, then they are in thermal equilibrium with each other. So to me, it seems kind of dumb, but I'm not a theoretical physicist. I'm theoretically a theoretical physicist. But to me, that's just a commutative property that you guys know from math. So that's pretty straightforward, I feel. The first law is where we're going to spend our time today. It says energy can neither be created nor destroyed. So if you just stop right there, that's just the law of conservation of energy. And really, the first law is a specific case of conservation of energy. Okay? Then it goes on to say it can only change forms. In any process, the total energy of the universe remains the same. Again, just conservation of energy. For a thermodynamic cycle, the net heat supplied to the system equals the net work done by the system. And so, what I was saying with this, what I was saying with this set of notes here is that the first law, like I said, is just really a specific case of your conservation of energy. I'm not going to ask you particular questions about, let's say, the 0th law or the 3rd law or whatever, but you should be aware of their existence. Then the second law, which we'll talk about at a later date in more detail, it says the entropy of an isolated system, not in equilibrium, will tend to increase over time, approaching a maximum value at equilibrium. So the second law is pretty simple. Like, the first law is going to be very confusing, as you'll see today, or can be very confusing. The second law is pretty straightforward. Entropy is a measurement of disorder or chaos, and so the more disorder or chaos you have, then the more entropy you have. But it has a lot of large, far-ranging consequences. So, we'll talk about some of those when we get to the second law in more detail. And then the third law of thermodynamics says that as a temperature approaches absolute zero, so as you get the system to absolute zero, the entropy of a system approaches a constant minimum, which basically means that, as you go to absolute zero, remember temperature is supposed to be based on the average kinetic energy of the molecules. So if absolute zero is the coldest you can get, that would theoretically be the point at which the average kinetic energy of your molecules is zero. And so it says that as you do that, the entropy approaches a constant minimum. So that'll be different for each particular system. And again, we're not going to get dive into this super deep or something, but in this class we focus mostly on the first and second laws, because again, the 0th I think is very simple and everybody should understand that probably before y'all got in here. And then the third is just kind of a weird one. But really, when you build something, it's going to be based on the first or second law. So let's keep going. So that's just a general overview of the 4 laws, before we dive in here. So first law, in equation form, looks like this. So it says the change in the internal energy of a system is equal to the heat added to the system minus the work done by the system, okay? So if you're just joining us, you really haven't missed anything other than me reading the first, or the 4 laws of thermodynamics. So the first law states, it's stated like this. So delta U, so delta is change. And so U is going to be internal energy, like your total stored energy. You may have seen U last year, represented for potential energy, but there was always a subscript on it, right? Like use of G or use of S, like for spring, for gravitational. So this is, you can think of like stored energy, but it's really stored in like the motion of your particles, right? So internal energy is going to be one of those things that's going to be, again, pretty impossible to know, because like you'd have to know the exact mass of every molecule in your system and its velocity, which is basically impossible to know. So that's why we don't try to find U. Notice that we try, this is delta U, the change in the total energy there. So we don't know what the total is, probably can never find it. But if you add heat, then that should increase your energy. If you take heat out, well, then that should decrease your energy. And so this is very critical here. That equals the heat added to the system. And then it should be written, or you can write this different way. This is the work done by the system. So essentially what's happening here is that if, let's say that this is 0, for example here. If I add heat to my system, in order for this to be 0, then the system does work. That means all that heat comes back out, or all that energy comes back out as work, right? And so you can write this as, minus W, because you're going to lose energy in that case. But the colors board, I believe, writes it like this, which is why I copied it. But you have to be very careful, because both of these numbers could be positive or negative, but they're not vectors. Let me start with that. None of these numbers are vectors, they're all scalars. But whether it's positive or negative, it is indicative if the energy is going into your system or out of your system, okay? Because if you add heat to the system, that would be a positive, that would be an increase in the energy of your system. If work is done by the system, then that would be a decrease in the energy of your system, right? Like negative, would take it away. So you got to be very careful if the energy is coming into your system or leaving your system. So, the thermodynamics of an ideal gas process, right? So we talked about those 4 processes last class, so now let's talk about more specifically how this is affected, or how the first law looks for these processes. So when gases expand, they do work on a piston. So here we have a chamber, we have a gas in here, and we have a piston that can move back and forth. So if the gas expands under constant pressure, right? We're not changing the pressure, we're doing something else. So we apply a pressure to this side, and pressure is force divided by area, so we can calculate that force. Then we will apply force over distance. That's work. That is the definition of work. Okay. So if the gas expands under constant pressure, pushing the piston from xi to xf, then your displacement is final minus addition, right? So it says right here, the work done by the gas, in this case, would be force times the distance. And we know that pressure is force divided by area. So if we solve for force, in that case, it would be force is pressure times area. Everybody see where that PA came from? And then the distance is, or your displacement is going to be your final position minus initial. So all I did here was take force times the distance and substituted these things here. But because force is pressure times area, now I can take this area and I can distribute it inside of these parentheses. So I get P is AXF minus AXI. And so if you have an area times another length, well, that by definition is a volume, right? And so that becomes, P times V final minus V initial, which is just delta V. So the work done by a gas can be calculated as the force you're applying to your piston times the distance the piston moved. But likewise, if we know the pressure that our gas is applying, which is much more likely for our ideal gas processes, we can multiply that times the change in volume. So the change in volume is literally like the increase or decrease of the volume of the chamber, right? And so hopefully you can see how that's going to be pretty easy to get those numbers from like those ideal gas things that we did last class. As a result, we also have our PV graphs, right? Our pressure versus volume graphs. And because it's pressure times volume, that means on those graphs, the work is literally the area underneath the curve of those graphs, okay? So if you ever need to find the work done by the process, well, it's literally just that area. So in some cases, it's an easy area to calculate, in some cases it's not. So for all ideal gas processes, the work is the area under the curve. So we just talked about that. No work is done during an isochoric process. So, okay, there's a couple of things here. So first of all, in picture A, it says for an isobaric process. So isobaric, remember, that's constant pressure, right? Iso, same, baric, barometric pressure. So if it's an isobaric process, this area is going to be super easy to calculate, right? Because you know your volume, or sorry, you know your pressure, that doesn't change, and then you just find your change of volume, just do, P times V, or delta V, boom, done. You got your work. Then it also says here, no work is done during isochoric. So isochoric is same volume. And so that makes sense because remember an isochoric process would just be a straight vertical line here. So that it would have no area underneath it, it's a line. So that also makes sense, right? And then the simple relationship of P times delta V applies only to constant pressure processes, okay? So if you're doing a constant pressure process like this, you can do P times delta V. If it's something else, like work done along an isotherm, it's still the area under the curve, but you can't just do pressure times volume because your pressure changes. Does that make sense? Now, if this was a more complicated class, then I would simply have you find the function here and do the area under the curve using calculus, but we're not doing that. So we can still find the area, or at least approximate the area, using regular algebra if needed. But most of the time we're not going to do that because you're not required to do calculus, basically. So you must use the geometry of the PV diagram to calculate the area. So if you need to do it and it's not just straight up a rectangle, then you're going to have to be like, well, this is kind of like a rectangle here, this is kind of like a triangle here, so I can approximate it, right? All right, so thermodynamics of an ideal gas process. So this is just trying to relate these different graphs to like what's happening here. So here we have a chamber, and here, so this is like saying, okay, volume 2, volume 1. So this is like the piston that's being moved around. It's like if the piston started out here, that would be like your volume 1, and then you do work, like you physically push it in from like point 1 to point 2, like you compress that gas here. And this is like the curve that it goes along for our random example. Hopefully you can see how like this is like the physical thing that's happening, and this ends up being the curve, right? So in this case, you would end up drawing a arrow actually on your graph. Well, you should probably have an arrow on each graph, unless it's unless it's a nice reversible process. But so like if you put an arrow on the graph, that indicates like this is what you physically did, right? Now, what's interesting here is that you could go from here to there, but then you could also go back, right? I mean, you could pull this thing back out if you wanted. In this case, like when you push it in, you're doing work on the system, you would be giving it energy. And then if you were pulling it out, well, you would be taking energy out of the system. And so for this kind of example here, let's say that it like went like this path to get back. Now this is a closed process, right? You can go around here, but here's the deal. Like there's an area under the curve here, right? And so if we went in this direction, kind of like that, this is the work that you did on it. Like that's the energy you put in. But then if you pulled it out like this total area here like this, is the energy that would come out of your system. So the net work in this case is the energy changed, right? Because both of these areas underneath here would end up canceling out, right? The energy you put in versus the energy you took out. Like this area would end up canceling out. So anytime you have a closed shape on your graph, indicates the work that is lost or gained by the system. Does that make sense? And whether it's lost or gained kind of depends on the direction this is flowing, right? Like if it was flowing the other way, then this would be the net work gained, but flowing this way is lost. Okay. So here, this is just a description of the picture, so hopefully I didn't say anything wrong. The work done is energy transferred out of the system, and the energy of the gas. Oh, so if the gas does work, like if we let it expand on its own, then the work done is the energy transferred out of the system, and the energy of the gas decreases. We often say the work is done by the gas. Work is done on the gas by an external force pushing the piston, right? So in that case, energy is transferred into the system as work, and therefore the energy of the gas increases. So work is done on the system. So if work is done on the system, there's an increase in the energy of the system. And if work is done by the system, that's a decrease in energy, right? So it's like an addition or subtraction on our first law. Similarities between work and heat transfer. Both are recognized as at the boundaries of a system as they cross them. So it's called a boundary phenomenon. Systems possess energy, but not heat or work. They're transfer phenomena. And both are associated with a process, not a state, right? Heat or work has no meaning at a state. And both are path functions. Their magnitude depends on the path followed during a process as well as the instance. So, what does this mean? Actually, it's not. So, you guys have heard pretty much all of this before, but I don't know how much it was emphasized. It's probably not emphasized highly. So, first of all, in order to do this, you have to have a system, right? So, in physics or really any science, you define your system. It's a set of objects, okay? If you think about these labs that you do, like, I know this year it's virtual, so it's a little bit more difficult. But you have to think about this. Like if you think about like the Boyle's Law lab, it was just really a piston, right? They had a chamber and you had like a piston here that you could like force it in there. So your system is really this piston here and all the air molecules in it, or whatever gas was in there. That's it. And one of the biggest troubles that a lot of students have is that they're like, if I'm like, hey, what was the system, right? Define the system. Tell me what things were part of the system. And they'll be like, everybody will be able to tell me, okay, the gas and probably the piston. But then they'll be like, well, but also like the pressure sensor. No, the pressure sensor is not a part of your system. If you use like a meter stick to measure how long something is, that's a tool that we use to make an observation, but it's not part of the system. Like, for example, if I just asked you to figure out how tall the school was, well, the school would be the system. Does that make sense? That like, no matter what you use to measure the height, it's not going to change the height of the school, right? At least that's the goal when we make measurements. So our system is really just the particles or entities, whatever we're talking about. So there's work and heat. So we can have one state here, and then let's say later on, we push this piston in or something. And so now our system has less room, right? We've changed the volume. What ends up happening here is that our system has, both a starting point and an ending point, right? That's what we defined last time. The end stage, beginning and the end. But they're path functions. So what that means is that the work added to the system, or the heat added to the system, or energy lost by the system depends on the path. So in that case, think of like friction. Like if you have, let's say, a ledge, like up here. If you take a brick and like shove it up this ramp to get it up there, there's going to be a lot of friction, right? Whereas if you just take like a brick over here and just simply lift it and stick it here, in the end, the box or the brick or whatever it is will end up with the same final energy. Does that make sense? Whether or not you go up the ramp or you just lift it straight up there. Does that make sense? Because it'll end up with the same gravitational potential energy. But since you are lifting it, the amount of energy you have to use depends on the path you take. Because all of your energy isn't going to end up in that box. Some of it is going to be burned off as heat, right? And if you lift it this way, like just straight up, it's going to require less energy because there's basically no friction, right? You're just lifting it and sticking it up there. Whereas if you take this box or brick or whatever it is and shove it up this ramp, you're going to have to overcome friction, against the ground to put it up there. And so in this case, you're going to have to apply more energy. Now maybe you can use less force, which is why you're doing it. But overall, you're going to have to use more energy to achieve the same goal. Does that make sense? And so friction, how much friction you use, how much energy is used, depends on the path. Does that make sense? And so just like that, heat and work are the same. Depending on how you get from point A to point B depends on how much work you get. And on those graphs that we were looking at, like our PV graphs, if you have point 1 here, point 2 there, well, you could go this way, or you could go this way, or you could go this way. But in each case, the area underneath these curves is going to be different, which is what we're talking about. Does that make sense? So, or you could go like straight down, like there's so many paths, and which path you take just kind of depends on your setup or which one you want to take. So they're path functions, so that's what that means. And then it also says here that systems possess energy. That systems do not heat or work. All right, they're a transfer phenomenon. And that's very critical because we don't use work and heat in our daily language, like we use them specifically in physics. And so the trouble ends up being that when you talk about heat or work in physics, because if you're just sitting there cooking something in your oven, you're like, oh, that's hot. That has a lot of heat. But that doesn't make any sense in physics, okay? Because in physics, heat is the energy that's physically transferred. If there's no energy being transferred, then there's no heat to talk about, right? So like you can grab, like the rack of your oven and burn your hand. You can be like, that gave me a lot of heat when I touched that oven. That makes sense, right? Because it's the energy physically transferred from the oven to you. But if it's sitting over there by itself, like all isolated, you can be like, it's hot, but it doesn't have heat. Or you could say it's heating up the room, it's transferring heat to the room current. Does that make sense? Because it's a transfer phenomenon. If something's not being moved from point A to point B, there's no work or heat being done, because they're both transfer phenomena, right? Because again, like if you think about work is a force times a distance. If you're just sitting there, like if your car is just sitting there not moving, it's clearly not doing any work, right? Like only work is being done when the car moves. We apply that force over the distance, which hopefully y'all got last year when y'all were in AP1. And you talked about work, and it was like, oh, if you apply 100 newtons of force to move your car and your car doesn't move, is work being done? No, because it's a process, right? And so it's the same thing here. So maybe I went too deep into this, but I want you guys to realize that. But they're both recognized at the boundaries of a system. So whenever you have a system, you define your group of objects as your system. You any energy transferred from one object to the other inside of your system is considered like an internal energy transfer. But like if we take energy from the outside and bring it in, that can be done as work or heat. Like you could add heat to the system, or you could push the system. That would be work or heat coming from the outside. But then if the system, like say expands or pushes something else, then it does work on the surroundings, right? And so that would be a loss of energy. So you have to think about the heat going in or the work going into your system, or the heat or work coming out, right? And you have to be careful here because the first law is really applying it to the entire universe. Sorry, that's conservation of energy. And then the first law just basically wants to narrow it down and look at just a system, because overall the energy is constant, okay? But here, we know that the total energy of the universe is constant, but for our particular system, we can put energy in and we can take energy out. And that would be across the boundaries of our system, right? And if you don't have a well-defined system, talking about heat or work transfer doesn't make any sense, right? Like in the case of like pushing your car, if your car is the system, well then you pushing the car, you can add energy to the car, you do work to it, you're giving it energy, but you're not part of that system. Does that make sense? I want to make a joke, I'm not going to. Okay. The thermodynamics of an ideal gas process. So, because thermal energy only depends on its temperature, right? That's the U. We can also write the change in thermal energy of an ideal gas. I'm not going to 100% explain this. It's just more math than I want to deal with at this point. But what we end up knowing is that the temperature is 2/3 your kinetic energy average divided by Boltzmann's constant. And so we can solve for the kinetic energy being as 3/2 Boltzmann's constant times the temperature. So this is an average kinetic energy. So the biggest problem with students applying this equation, like here, is its average kinetic energy. So like if you were looking at the average kinetic energy of the molecules, which you could find, and we talked about this, like last week, this is really the average kinetic energy per molecule, not like the total, okay? And so, if I was working on the math here, you essentially start with 1/2 mv squared for kinetic energy, and then you substitute things out. And most of that can be done pretty easily. I think that's something you can easily do yourself. And you can get Boltzmann's constant and temperature in there, but the 3 is the thing that most people don't see coming, okay? Because if you're just simply looking at equations that you've been given in the past, I feel like you can logic your way to 1/2 Boltzmann's constant times temperature. You can't logic your way to 3 just by looking at the equations. The 3 comes from the fact that we live in 3 dimensions.
That's crazy.
I know. But essentially you can have a kinetic energy, in this dimension, in your horizontal, vertical, and, the 3rd spatial dimension. So that's essentially where the 3 comes from. Like I said, I'm not getting into all that math, but it makes sense when you realize like you can have kinetic energy in 3 dimensions. And that's basically where the 3 comes from. So here you're changing energy, E. We can use the ideal gas equation along with this, and we get 3/2 N, the total number of particles, times Boltzmann's constant, is equal times our change in temperature. And this is 3/2 little n R delta T. So remember, big N is just number of molecules, and little n is number of molecules per mole. Right, or sorry, not per mole, number of moles, right? So, obviously here, this is just a switching between like R and KB and, the two N's. But this is kind of like total energy, and this is like average. So essentially to get from like here to there, well, not essentially, you can see like you need the number of molecules. Because this is like average energy per molecule, then if you knew how many molecules you had, well, you could essentially find the total energy change for a change in temperature. I explicitly write this out in the notes because there occasionally are problems where it asks you to do stuff like this, and it gives you like this information, but then you're like, I'm not really sure how to jump from here to there. Well, it's just the number of particles, or probably more specifically, you're going to know the number of moles. Because let's be honest here, if you know how many particles you have, that's just a weird thing. I have 4, oxygen atoms. Like, nobody knows that. So phase changes. So we've talked a little bit about this. In this class, we're not going to dive terribly deep into phase changes, but let's talk about it for a second, because you guys know that these things happen, right? So here, if we have a graph of temperature versus time, let's say that we start with, our solid form, let's say it's ice. If you place ice cubes into a sealed container and then heat the container, so a sealed container, that means, you can have a gas in there, but like no gas is coming in from the outside and mixing with it. If you put ice in a sealed container and put the lid on it and then start to heat it, well, eventually the temperature is going to go up. So basically, as you add temperature to a system, or add heat to a system, it's going to increase the temperature, right? Add heat, increase the temperature. Add heat, increase the temperature. That's true until you get to a phase change. When you're doing this, if you keep adding heat, you're not going to change the temperature at the melting point, okay? Because what's happening there is you're still adding energy into your system, but instead of it, increasing the temperature, the energy at a phase change point is going to breaking those molecular bonds, right? So for like a solid, it's going to be breaking the bonds of the crystalline structure that make up your solid. And the thing is like for something like ice, which melts into water, that what you guys should know is that once you have ice in water, let's say you take a cup of water, add some ice to it, the ice will melt pretty rapidly until they're at the same temperature. Once they're at the same temperature, they want to stay that temperature. And at 0 degrees Celsius, or 32 Fahrenheit, that's the temperature your cup of ice water wants to stay at until all of the ice is melted, which is the whole reason why we put ice in water or beverages in general, is because it will maintain that temperature until all of the ice is gone, okay? Because you'll add heat, so in terms of your cup, the heat comes from the environment, and it's going to try to warm it up, but before it can warm it up, it has to melt all of the ice, right? Once all of the ice is melted, then as you add heat, we're still adding the heat the whole time, now our temperature is going to start to increase again, okay? And so for most of the time, if you have a system here and you're adding heat, it's going to increase the temperature. But then, if we have liquid water, then we're going to hit a second phase change boundary where we can add more heat, but it's not going to increase the temperature. In this case, this is the boiling point, right? We're going to add heat. But essentially, as long as you have liquid water, the energy is going to be used to cause those molecules to get enough energy to escape this gravitational pull state, but at least overcome it for a bit and jump up into a gaseous state. And so as we add energy here, the molecules don't really get hotter until they can all boil away. So we talked about this before, that when we have water boiling in a pot, the reason why so many recipes call for boiling water is because it boils at 212 Fahrenheit or 100 Celsius, at standard pressure, and it will stay that way until all the water is boiled out of the pot, right? So that's what's happening here. So for most of the time, we're going to be focused on, these areas where we don't have a phase change. Now, technically, if you want to get technical, these are the three most common states of matter. There's more than three. They're up to like 8 or 9 total states now. We're not going to talk about pretty much any of those. I will give a brief shout out to plasma because it's pretty easy to understand given this, because essentially if you keep taking your liquid here that turned into a gas and keep adding energy to it, what's going to happen? Well, eventually, if you keep heating it, it'll undergo another phase change. And at that phase change, it's where a gas becomes a plasma. And here, I think it's easy to understand, like, the first phase change, going from a solid to a liquid, you're breaking the bonds of the solid molecules, right, that crystalline structure. Then going from a liquid to a gas, you're simply getting enough energy for the thing to overcome, Earth's gravitational pull and fly up into the air. Because they're not really bonded together. Now, in the case of water, yeah, there's some like weak hydrogen bonding and crap happening. So that does have to be overcome too in the case of water. But when you heat it up even more, what's the next bond to break? Well, if you know what a plasma actually is, it's pretty obvious. A plasma is just a sea of charged particles. Well, how do you get those charged particles from your neutral atom? Well, essentially what happens is you keep adding energy to this gas, and eventually the electrons themselves, not just the valence ones, I'm talking about all of the electrons that orbit your atom. If you keep pouring in enough energy, those electrons will be going fast enough that the force, the electromagnetic force between your positive protons and your negative electrons won't be strong enough to hold the electrons in orbit anymore, and the electrons will whiz free. And essentially, that's what a plasma is. It's a sea of positively charged particles with electrons just running everywhere. That's what a plasma is, and that's what the sun is, because it's so stinking hot. And so I think those 4 phases are pretty easy to understand in terms of you simply keep heating stuff. So it says here, example 1, if you heat a substance in an insulated container, is it possible that the temperature of the substance remains unchanged?
Yes.
Yes. When?
Changing.
Yeah, it's changing. Yeah. Example 2, a student gives the following description of a thermodynamic cycle through which a symbol of ideal monatomic gas is taken. Initially, the gas has a volume of 1 times 10 to the negative third meters cubed and a pressure of 1 times 10 to the fifth pascals. The gas is in a closed cylinder and it has a movable piston on one end. Call the initial state of the gas state A. The process AB takes the gas at a constant pressure from state A to state B, where B has 3 times the volume of state A. The gas is then compressed isothermally until it is back to its initial volume, reaching state C. Then finally, a single process CA returns the gas to its initial state A. So it says here that on the axes below, to the side here in this case, plot states A, B, and C, and then sketch a graph of the pressure as a function of volume for cycle A, B, C, A. Label states A, B, C. And the axis with numerical value. So this is essentially the end of the notes. This is kind of like a free response problem. It doesn't have the whole problem here because we're not done with thermodynamics. But I want you guys to see that some of these problems, you look at these free response problems, you're like, oh man, that's too much. I can't do that. But that's a lot of words, sure. But essentially it just wants us to make a graph. Does that make sense? You guys should be able to do this. So I'm going to be your pen. So you guys tell me what to write here. So it gives me this thing. It says that it's already given us axes, and it's given us that this is pressure times 10 to the fifth, and this is volume times 10 to the negative third. So let's start at the beginning. Where is state A?
Top right corner.
top right corner. So y'all want to put it like here?
Right. Well, no, it's 1 to the times center of the bed, it's the bottom left.
Oh, yeah, no, yeah.
Oh, yeah. So that brings up a good point. Should we
Right.
scale it first or should we plot it first? Like, should we write numbers here?
No, we just
What
count
should we
by
put?
1, it's only goes up to 3.
Huh?
It's just counting, but we just count by 1, it's only going to 3.
So you want to count by 1? So like 1, 2, 3, 4 here?
Sure.
Y'all want to do the same thing over here?
Yes, yeah.
So it says 1, 2, 3, 4, but remember this is like 1 times 10 to the 5th, this would be 4 times 10 to the 5th, and so on, right?
Yeah.
Okay, so where should we put this point then? The first one, it gives us
1,
1, right? So we'll put an X. Try to put an X. So it should be right there on that line, but forgive my,
It's supposed to be A.
yeah, so that's point A, right? So I'm gonna label it point A. There we go. All right, so now where is point B then?
3 times the volume, so 3.
3, 3, 1?
Yeah, it's got constant pressure.
So that's point B. Constant pressure, so my process, that blue, my process would essentially be that, right? So that looks like a constant pressure process going from A to B, where we end with 3 times the volume, right?
Yeah.
So then where is C?
Isn't it like A? Oh, this is where the is.
Which one's isothermally?
So isotherm looks like a what?
It's like the curve.
Yeah, it's a hyperbolic curve.
So do a hyperbolic curve back to A, but the pressure, would the pressure rise?
Okay, so hopefully you guys understand, I can't go from B to A, making a hyperbolic.
Yeah, so,
So C can't be at this point.
well, not at A, but it'd be higher, it'd be on the.
So are you trying to say the same
So,
volume as
Yeah,
that?
it's the same volume, so.
Same volume, so then, I know it's gonna be on this line, so where?
I'm not sure where the pressure would be though.
Okay. But it's compressed isothermally until it's back to its initial volume, reaching state C. The final process, CA returns its gas to initial state A. So we've got B and, we got A and B, so C, we know it's gonna be something, some sort of curve, but is it like, do I curve it to 2, do I curve it to 3, do I curve it to 4, or maybe somewhere in between those? Well, how do we figure this out?
The whole box. I just know it curves back to 1, I don't know which pressure it's supposed to be at.
Okay. Well, do we have any way of figuring that out? We do.
Okay.
We
Maybe
do.
Any formula we could use?
We do have a formula we can use.
Was it
PV over T? Can we do that?
What do you mean by
Or the, what's
PV
the-
over T? That's like half the formula. That's what
equals PV over T.
Okay. So you're talking like initial versus final. Maybe. It's definitely a thought.
Okay, we're starting at B.
So we're going from B to C, right?
From B to C.
So essentially, I can put B's here and C's there. Okay. So what do we know is true about B to C? First off, what does it say?
The volume's the same.
What's the same?
The curve back.
So it's an isotherm, right?
Yeah.
So we instantly know these two are the same, right? Okay. So we know our pressure and volume that we start with. Do we know pressure or volume that we end with?
Yeah, the volume
The
is
volume.
the same as
Okay, so we could solve for a final pressure then, right?
A. Yeah.
So if initially we're at B, so P, pressure at B is 1 times 10 to the 5th, so 1 times 10 to the 5th pascals, times V, so the volume is what, 3 times 10 to the negative third? Meters cubed. Equals this pressure, that's point C, I'm going to specifically say C, times something, or 1 times 10 to the negative third, right? Because that's our volume at that point. Oh my gosh, okay.
Wait, it's times 10 to the 5th, not negative 30.
Well, no, it's pressure,
Yeah, you're right.
So it's times volume.
Oh, no.
Okay, yeah, I think, well, I'm gonna just put all the pressure in there, so then times 10 to the negative third meters cubed. So, well, what's 3 times 1?
3.
What's 10 to the 5th times 10 to the negative third?
Into the second.
In a second. And I know that the units can do a thing, but I'm just gonna make the units just multiply each other, right? For simplicity's sake, right? Times 1 to the 10 to the negative third, right? Cubed. So then I should divide by 1 times 10 to the negative third meters cubed. Divide by 1 10 to the negative third meters cubed. So meters cubed cancel, right? And so then what's 3 divided by 1?
3.
What's 10 to the second divided by 10 to the negative third?
10 to the 5th.
Fifth. Oh, fifth. Pascals. So 10 to the 5th is our scale. So 1, 2 must be right there.
Wow.
Wow. And so then, we kind of go, something like that.
It is.
So that's process BC, and then it says CA, it goes, returns the gas, well, a single process CA returns the gas to its initial state. Well, that must be straight down, right? Because we're straight above it. So we know, and what's interesting here is this is just part A. Obviously, there's going to be other parts to this problem, but
Does the second upper
yeah, this is like the very first question of an FRQ. And so what I want to show you guys is that like these FRQs, again, they all tend to build on each other. But what's interesting is it didn't actually tell us the process from CA, just as it goes straight back to A. But we know by looking at this graph that that is an isochorous process, right? Look, sure.
Which one's isochorous?
The constant line.
What?
I thought the isochorous was the line down, like straight up and down.
Yeah, that's this one. That's the one back.
Okay.
Yeah. So what I'm trying to point out is that it didn't actually say that, but because we made the graph, it's very obvious that's what it has to do. What it has to, because it says one right here, a single process, right? So since it says a single process and it's at the right volume, just not the right pressure, so we just keep constant volume. Does that make sense? Okay. So keeping on here. So here's the answer. Now notice for this particular problem that actually is 3 points. So this is for a straight line from A to B, an isotherm from B to C ending at the right final pressure, which must be labeled 3 or C. So it has to be this pressure labeled at 3 because you should be able to find that, right? And then it's a curve that must be obviously concave up. So when you're drawing these curves by hand, they don't expect this to be like a perfect, hyperbolic curve, but it should be obviously curved like that, And then it's another point for a straight line from C to A with a state labeled 1, 1. So here, notice we skipped part B. It says use the student's verbal description or your graph in part A1 to calculate a numerical value for work done by the gas process in AB. So here, I just saw somebody said that in the chat, that was useful. It wants us to calculate the work done for process AB. Well, that's just the area under the curve, and since it's a constant pressure, well, we just do 1 times 10 to the 5th. Times this change in volume, which is just 2 times 10 to the negative third, right? So now notice that this is a loss of 200 joules. Why is it a loss?
Because the gas is doing work done.
Work done by the gas, right? So it doesn't explicitly, like in this formula, there's no negative, but it does say, calculate the work done by the gas. So you have to know, like, okay, that energy had to come out of my system, right? So essentially on graphs here, let me go back to this graph. If the arrows are pointed, to the left or like left up or whatever, then the energy is going to come out of your system. And if the arrows are pointed to like the left or up, then the energy is going into our system, right? And obviously if it's pointed straight up or down, that's not an energy transfer. It's not work, right? Because there's no work done underneath the law. This is calculate the magnitude of the change in internal energy for process A, B. Or no, it says calculate. It doesn't say calculate. It just says the magnitude of the change is delta U, is 300 joules. So it just gives us that. Then it says calculate the numerical value for the energy added or removed from the gas in heating process A, B. So now this one we haven't really talked about, but that's why it's here. So we know that the first law is delta U equals Q, the heat, plus our work, right? So we just calculated that the gas lost 200 joules of energy here, right? And it says this is all during process A, B. And then it says in this part 2, it says the internal energy changed by 300. So we know that this thing, delta U, is 300 joules, right? And it wants us to calculate a numerical value for the energy added or removed from the gas by heat. So we're trying to find the heat. We're trying to find heat.
So that's just 300 plus 200?
Yeah. And so because we lost 200 in this part, but overall the energy of the gas gained 300 joules. Well, if the overall gas gained 300 and it did 200 joules of work, well then we must have added 500 joules of energy to supply this. Does that make sense? So what's interesting is in this graph, it doesn't show us the heat. Okay? Like nowhere on the graph does it show heat. So we can see work on the graph, we can see, these different processes, or whatever. We can see the processes on the graph, but we can't see the heat. Okay, so the heat, in some of these processes, the heat will be constant, sometimes it'll be changed by the process, but that's not something that's directly on the graph, right? It's not something that's graphed. It can be something sometimes we can infer, but a lot of times it's just going to be something that's either given to us or we can solve because we know the other stuff. Okay, this is a very important slide. So we have our 4 processes, right? Isochoric, so that's constant volume, isobaric, constant pressure, isothermal, constant temperature, adiabatic, constant heat, essentially. So how does this change our first law? Well, the first law is always delta U is equal to Q plus W. So isochoric, if it's an isochoric process, so on our graph, that's a straight vertical line. Therefore, no work can be done. Well, that's very obvious that means work is 0. Go back. Work is 0, so delta U just equals our Q. So if you can figure out how much your energy changed, that is the heat, because there is no work done. So if heat was gained or lost, that's going to be just explicitly what is gained or lost by your system, right? Because no work is done. Then isobaric, you got to know, okay, well, isobaric, that's our constant volume process. And with constant volume was the first one, constant pressure. That's our constant pressure process, so that's our flat horizontal line. I made the horizontal line with my arm, but I said something wrong. So that's work done or by the system is equal to pressure times energy. Pressure times volume. So that, in this case, it doesn't really simplify our equation, but remember that isobaric is the only one where we can very easily calculate the work from the graph. Right? It's just force times distance or pressure times volume or change in volume. So that's very easy to find from our graph. So it doesn't really simplify the equation itself, but if we have a graph along with this, then we can usually very easily find the work. All right. Isothermal, means that no energy enters or leaves the system. So an isotherm means that delta U is 0. Okay? So if you're looking at the isotherm, the only time energy can be added is, enters or leaves the system. Delta U is 0 on an isotherm. Okay? So that simplifies our equation to being that, delta U is 0. Well, then the Q must equal W, right? So in this case, like if let's say our system does work on the isotherm, in order for our system to do work, we have to be adding heat constantly, and the system is just instantly converting that heat into the work being done, right? So they're obviously, one's flowing in and one's flowing out, but which one's flowing which way depends on, the process. And then last but not least, adiabatic. No heat is transferred to or from the system, i.e. Q equals 0, right? That's the definition of adiabatic. So then our first law just becomes delta U equals the work, right? So if you're doing work, like if you're shoving your piston in, then that instantly translates into an increase in the internal energy, which would increase the temperature, right? So, this is a very important slide, and you need to learn these, because essentially it simplifies the first law, and so you can look at these different processes and go, okay, for this one, this is happening, for this one, this is happening, and we're going to use all of these together, probably not the same problem, but usually several of these are going to happen during the process of one problem. So, for example, a thermodynamic system is taken from initial state X along this path X, Y, Z, X, that's shown in the diagram. So first of all, the process X, Y, and Y, Z, those have very specific names. Does the process ZX have a specific thing? Is that like an adiabatic process or something?
No.
No. And that's fine. Just remember that we don't have any special rules for ZX. And a lot of times on these graphs, the whole reason why they do that is just so we can get a closed shape that is easy to calculate. Because, if they did like some, obviously there's not going to be an isotherm or anything on Z to X, but they're just, just basically cutting it there to make things easier for you. So then it says for the process X to Y, delta U is greater than 0, and, so it tells us right now, go over X to Y. First of all, is that isobaric, isochoric, adiabatic, isothermal?
Isobaric.
Yeah, isobaric, right? Constant pressure. So constant pressure, does that mean our heat equals 0? No. So if the heat doesn't equal 0, so A, C, and D are all wrong then. So the heat should be greater than 0 and the work should be less than 0. So in the case of X, Y, the arrow is pointed to the right. So the system is going to be doing work. So yes, it's going to be losing energy in that process. But it says that U is greater than 0. Well, in order for U to be greater than 0, it's just like the example we saw before this, energy has to be coming into the system. So Q has to be not just greater than 0, it actually has to be, greater than the absolute value of the work done, right? Yay. Okay, I think that's the end. Because it's not going any further. So I'm going to stop this.